lesson, I'm going to be talking about electromagnetic radiation. Now, you might not think you've ever experienced electromagnetic radiation, but actually you're experiencing it right now by watching this video, by heating up your hot pocket, by listening to the radio, by doing anything that you do on a daily basis. You are using electromagnetic radiation. So one example of electromagnetic radiation is light. So the fact that you can see all these gorgeous colors on this screen, hopefully, is because of electromagnetic radiation. Visible light, what you can see, all those gorgeous, that rainbow of colors, that is a form of electromagnetic radiation. Another form of electromagnetic radiation is microwaves, radio waves, infrared rays, UV rays, right? When you get sunburn, it's because of the sun, the UV rays, X-rays if you've ever broken a bone. So looking at this, there are three different quantitative values I can give for this these waves, this electromagnetic radiation. The first one is wavelength. Okay, so the distance, wavelength, is the distance from one crest to the next. So if you look on the left-hand side, far left-hand side of these waves at the very top, those have the highest wavelength because there's the greatest distance between your crests or your peaks. Okay? And the unit for that is going to be meters. Now, the ones on the right-hand side, they have the shortest distance between those crests, those peaks. And so they have small wavelengths. Now, the symbol for wavelength is going to be that lambda symbol right there, and the unit is meters. Now, frequency is the number of times a crest, so that peak, will pass a point in 1 second. Okay? And so the unit for frequency is hertz, or seconds to the -1, which we'll address in just 1 second. But the representation in a formula we're about to use is that nu symbol. It looks like a V. All right, so we've got wavelength, we've got frequency. The last one is going to be energy. So if you notice, when you have large wavelengths far to the left, those are lower energy, while if you have very short wavelengths, then you have high energy. Okay, so if you look even just at red versus violet, red light has the lowest energy but the largest wavelengths, while violet light has the highest energy but the lowest wavelength. So let's talk about the relationship between these two, wavelength, frequency, and energy. How are they related? Well, wavelength and frequency are inversely related, meaning the higher your wavelength, the shorter or the smaller your frequency. So for example, if you look at the very top again, on the far left, those have large wavelengths, but the number of times that a crest is going to pass a point, that's going to be much less than as you move to the right and you have higher frequency. So wavelength and frequency, when one goes up, the other goes down. So that's an inverse relationship. Now frequency and energy, the higher your frequency, the farther to the right you are on that graph right there, the higher your energy is. And so they are directly related to each other. Okay? And so wavelength and energy are going to be inversely related. The lower the energy, the greater the distance between those crests. So let's numerically talk about this. The formula for relating frequency and wavelength is C equals lambda times nu. All right, C, what is C? C is your speed of light. C is 3.00 times 10 to the 8th meters per second. So no matter what the wavelength or the frequency is, the speed of light will always stay the same. The wavelength, represented with that lambda, the units for that are meters. Okay? And then frequency, the units are going to be either seconds to the -1, because it's the number of times per second, or hertz. So those units are interchangeable. So let's look at an example. Here I give you the frequency, so we're going to use this formula. I know that my speed of light is 3.00 times 10 to the 8th meters per second. Okay? That equals, well, I don't know what lambda is right now, that's what I'm solving for, times my frequency, which is 1 times 10 to the 14th seconds to the -1. And so to find my wavelength, I'm just going to divide both sides by 1 times 10 to the 14th, and I get 3 times 10 to the -6, and my units for wavelength are meters.